Okay, thank you for the introduction. So I'll be talking about the security of signatures and encryption against quantum attacks, and this is a joint work with Boneh. All right, so for signatures, the standard notion of security is security against what's called a chosen message attack. Here, the adversary sends over message M and receives a signature on that message. After doing this many times, the adversary tries to forge a signature on a new message. Well, we're in the quantum session, so we might as well give the adversary a quantum computer. And we get the following picture, which is what most people think of when they think of signatures secure against quantum adversaries. The adversary still sends over messages M and receives signatures sigma, but in between his queries, he's able to use his quantum computer to solve problems like factoring or discrete log. Stress, though, that the actual chosen message part of the attack is classical, and it turns out that many times classical proof techniques just work in this setting. For this talk, I'll be talking about an even stronger model called the quantum chosen message attack. So here, consider the case where not just the adversary, but the signer himself is quantum. Since everyone is quantum, it may be possible for the adversary to submit not just a single message M, but a superposition on all messages. So think of the superposition as a state that's simultaneously every message in the message space, where each message has its own weight. The signer then signs the entire superposition. And this roughly means that the adversary sends back a superposition on signatures over all messages, where each signature has the same weight as the corresponding message in the adversary's query. Now, the interactions themselves are quantum, and so we really do need quantum proofs of security. Okay, so from this point forward, when I refer to quantum security, I refer to this model, and when I refer to classical security, I mean the model from the last slide, where the chosen message attack is classical, but the adversary has a quantum computer. Okay. So this whole idea of taking classical crypto and trying to attack it with quantum queries is a relatively new and emerging field. We've already seen several primitives analyzed in this context, but there is a lot more work to be done here. You might wonder, why do we care about these kind of attacks? Well, we don't know what the world's going to look like when we have quantum computers, and it's going to be very difficult to anticipate all of the funny quantum attacks that adversaries might try, so it makes sense to use the most conservative security model available. One possible objection is that we can always classicalize queries. And what I mean by this is that when the adversary sends over his superposition, we can measure or observe that superposition. And this has the effect of selecting one of the messages in the superposition at random and collapsing the entire quantum state to just that single classical message. And now all the signer has to do is sign a single message, so we've basically turned the adversary's quantum attack into a classical attack. Unfortunately, this classicalization step might not actually be as easy as it sounds to implement and could perhaps be a substantial burden on the hardware designer. Moreover, it's a physical layer of security, and maybe an adversary is going to be able to bypass that. We still want to maintain security even in that case. So our answer is to use quantum secure crypto, and if you do this, you don't need to worry about this physical classicalization step. All right, now I need to actually briefly be a little more careful in defining security. So the problem is that in the classical setting, the adversary's goal is to construct a signature on a new message. But in our setting, the adversary gets to see signatures on a superposition of every message. So in a sense, no messages are new. Instead, we observe that after each query, the adversary can just measure the signature response, and he'll get a signature on a random message. After doing this Q times, he'll get Q signatures. And we want it to be hard for the adversary to produce even an additional signature. So we define a forgery as the event that the adversary produces Q+1 signatures. And we say that the scheme is secure if no efficient quantum adversary can accomplish this task. Okay. Our first result is that there is a separation. We show that there are schemes that are secure against a classical chosen message attack, but are insecure once we allow the adversary quantum queries. This shows that these quantum attacks do give the adversary more power to attack the signature scheme. Now, as far as actually proving quantum security, there are several difficulties. One of the classical techniques for proving security is to separate the message space into two sets, a good set of messages that the reduction will be able to sign and a bad set that the reduction will not be able to sign. And if the reduction algorithm ever is faced with one of those bad messages, it just aborts. But now in our setting, the reduction algorithm is going to get a superposition of all messages, some of which are good, some of which are bad. It's not really clear what we do. Do we abort? Do we do something else? I mean, one obvious option is to try to just sign the bad messages with junk. But it turns out that the adversary will be able to detect that we sign these messages improperly. Another issue is that existing techniques for proving quantum security always leave the adversary's query intact. And in some other works, it's already been observed that these kind of proof techniques have some fundamental limitations. And in the case of signatures, just for example, it's impossible for these proof techniques to prove security for unique signatures. Okay, but we really want to build signatures that are secure against quantum attacks, so what do? Well, the obvious place to start looking is at the classical constructions. For example, constructions from lattices or in the random oracle model, or even from generic assumptions. In our work, we show that in many cases, we can actually take classical schemes, tweak them slightly, and get schemes that are secure against quantum attacks. The example I want to show is the hash and sign signature scheme. Here, we just hash a message down to a small hash h and sign this small hash with some small signature scheme S prime. Classically, there are several advantages, one of which is efficiency. But importantly for this talk, the security requirements for S prime are rather weak. And if we were to model H as a random oracle, and even if we have a weak signature scheme S prime, we can still get the full chosen message security for S. So our goal is to see if this sort of boosting of security actually holds in the quantum setting, and if we can take a classically secure S prime, put it into the hash and sign scheme, and get out a quantum secure S. Well, let's see what the attack looks like on the hash and sign. So the adversary submits a superposition. Those get hashed to a superposition of hashes, and then that superposition of hashes gets signed. After the adversary does this many times, he produces a bunch of signatures with some non-negligible probability epsilon. Our goal is to take such an adversary and turn it into an adversary for the classical security of S prime. And as a first step, we need to be able to simulate the view of the adversary. This is actually problematic, though, because there are exponentially many hashes in the hash superposition. And in order to sign them, it seems like we need to figure out a signature for every single hash. And if we're only allowed classical queries to S prime, that's going to take too long. Instead, we use a tool called small range distributions, which we previously introduced in the context of pseudorandom functions. So let's let P be a random function from the message space into the integers 1 to R, and let Q be another random function from the integers 1 to R into the hash space. Consider the composition of P and Q. Its domain and codomain are the same as the random function H from the previous slide, and yet the range of this function, the number of points, possible point outputs, is relatively small. It's only R points. Nonetheless, we've previously shown that if we choose R to be a large enough polynomial, we can actually get that these small range functions are indistinguishable from truly random functions. So we as a first step, we just swap out our random oracle with small range functions. So instead of applying a random function h, we apply our random function p to get a superposition of integers in 1 to r, and then apply q to get a superposition of hashes. And then we just sign the hashes. Now, the adversary success probability decreases a little because, potentially decreases a little because p composed with q is not truly random, but it's indistinguishable, so it still succeeds with probability, say, epsilon over 2. But now the key is that the hash superposition is only a superposition over q hashes, or sorry, r hashes. And so in order to simulate, we only need to make r classical queries to S prime. Okay, but we're not done. We need to show, now that we've simulated, that we can actually use one of the adversary's forgeries as a forgery for S prime. But unfortunately, the adversary gives us q+1 signatures. But we had to query S prime r times in order to simulate. And it turns out that r is much, much bigger than q, so we don't really have any guarantees on whether these signatures are new or not. To overcome this problem, we introduce a new technique called intermediate measurement. So just take some general quantum algorithm that solves some task and open it up at some point in its execution. What you'll see is a bunch of qubits. Let's logically separate those qubits into two sets, a small set that I'll call x, and the rest of them which I'll call y. What happens when we measure just the x qubits? Well, the x qubit superposition will collapse into just a single string x, and afterward we can just resume the algorithm as if we didn't do anything. Suppose, though, that the number of outcomes of our measurement were t. We show that the success probability of this new algorithm, obtained by pausing, measuring, and then resuming, is still pretty high. It's only been reduced by a factor of t. Okay, so what do we do in order to break the security of S prime? Well, when the adversary submits his message superposition, we still apply p to get a superposition of integers in 1 to r. But now we just measure that superposition and get just a random value in 1 to r. Then we apply q to get a single hash and sign the single hash. All right, so we had to do this q times, one for each of the adversary's queries, and each time the measurement had one of r outcomes. So combining this all together, we get that the adversary success probability is epsilon over 2r to the q. Let's ignore the probability for a moment and just look at the case where the adversary actually succeeds. Well, he gives us q+1 valid signatures, but we only had to query S prime q times, one for each of his queries. And so it must be that one of those q+1 signatures is actually a forgery for S prime, and therefore we have successfully broken S prime. Now, this epsilon over 2r to the q is relatively small, but if we fix q to be a constant, then it's non-negligible, and we have then proven the security of S. Okay, but what do we do about many-time secure schemes? Well, we actually end up tweaking the hash and sign scheme just a little bit in order to make it many-time secure. The two changes we make are that we salt the hash, and then we're just careful on how we generate the randomness used for the small scheme S prime. And by making these two small adjustments, we are able to prove the quantum many-time security of S, assuming only the classical security of S prime. All right. Now I'm just going to briefly discuss our other signature constructions. We also give a very slight modification to the GPV signature scheme and prove that it is quantum secure. Now this scheme and the one on the previous slide are both in the so-called quantum random oracle model, but we also give two constructions in the standard model. Another generic conversion where we basically just swap the random oracle with a chameleon hash function, and then we also give a construction from generic assumptions. All right, so that's all I have for signatures. Now I just need to briefly go over our results for encryption. The model we consider for encryption is the quantum chosen ciphertext attack. So this is a generalization of the classical chosen ciphertext attack, where the adversary is able to learn decryptions on ciphertexts of his choice. on superpositions of ciphertext of his choice. Though, for reasons I will not be able to get into, the adversary's goal is still to break the classical semantic security of the encryption scheme. Okay, so what do we show? Well, just like in the case of signatures, we show a separation, and therefore the quantum chosen ciphertext attack really is a stronger attack than the classical attack. Nonetheless, we give two constructions, one in each of the symmetric and public key settings. All right, to summarize, we show for both signatures and encryption that classical security is weaker than quantum security. Nonetheless, we give a handful of signature constructions that achieve this strong notion of quantum security, as well as a couple encryption schemes. For open problems, it seems interesting to try to prove security of existing constructions. For example, Fiat-Shamir signatures. Or outside of the realm of signatures, how about various MAC constructions like CBC MAC, NMAC, or PMAC? All of these schemes lack a quantum proof of security. All right, that's all I have. Thank you very much.